Welcome to a lesson with Dr. Powell. Let's take a look at another type of airdrop map, but this time on columns. So what is that going to represent? So when we did stuff with like a row operation, we took this whole row, we lifted it up, multiplied it by something, and then landed it down here and plop and see what happens here. We can look at this matrix and do some things to it and change it so we can see it in another form. Um, Yet, if we're looking at, but if we want to do column operations, think about what that would be. Like maybe we take this whole column, we multiply it by something, airlift it, and then drop it on something right here and see what happens. It's kind of similarly doing that basic type of thing. Well, um, if we thought of the row interpretation of matrix multiplication, that actually works great. It actually would be the same basic type of thing as what we're doing in the column interpretation. Because we're just changing everything. So we're looking at columns doing things instead of rows. And so really what we'd get is we think this is a map that goes from R3 in the row interpretation, so R3 in and R4 out. And then over here, we input this into something, an airdrop map, and we'd be going R4. Using the same basic type of logic, we could airdrop it, and that'd be the same thing as isomorphically looking at the row interpretation and getting something on this side. Well, that's great. So we get a matrix over here, which represents an isomorphism. Now, wait a minute. If we change our interpretation back after we did that to the column interpretation, this is still an isomorphism. In fact, it's an isomorphism that happens before this map. So now we're going to get an isomorphism before the map, and then that's going to output R3. So we just kind of changed it now using the airdrop map idea from the row interpretation, but using it now as an isomorphism going this way, in this direction. Then we end up, then our column operations end up being something that we're doing on our domain before we run this function. So our column operations happen before. They happen from here. And notice that should work just fine because what are these? I mean, these are the images, like this is the image of E1, the image of E2, and the image of E3, and the image of E4. And think about what happens here. If we perform an airdrop operation, it's kind of like saying you take you take everything in here. In fact, let's just kind of think about that. You take something in fact, you take this whole column, maybe you multiply it by something, in fact, let's multiply it by a specific number. Let's multiply it by -2, and then let's plop it. So we take this guy and let's plop it on top of f of e3. All right, so just take that and plop it in f of e3, and maybe that's going to be the new f of e3, and all the other guys stay the same. Now think about what's going on. What we're doing is, since this f is a nice linear transformation, I can put all this on the inside of f. And then see what I've done? I've actually done something to the codomain. To the domain, I've done something to the domain. And then what I've done to the domain kind of transfers to the codomain. So doing column operations is actually doing stuff before the map. So it's actually building an isomorphism before the map. An airdrop map of columns is an isomorphism that happens before. So given a matrix, we can actually change it to isomorphically kind of see what it looks like, maybe in another setting. By running maps before, and this is one example of that. It's an airdrop map of columns, and likewise, we can have maps afterwards, which are row operations. So row operations and column operations can work together to change a matrix into a nice form. Now, before we leave this lesson, let's just kind of mention maybe what our end goal might be by running row and column operations. maybe we would end up seeing something like this in the end. Maybe, what if we were able to run some row and column operations and end up getting this as the resulting map? So we start with a matrix, maybe call it A, it's a function, vector spaces from R4 to R3. And then maybe in the end, we do some row operations to it, some column operations. So basically, we do an isomorphism after and before. All right, so we still have the same codomain and we still have the same domain. And then as we run it, maybe the resulting composition looks something like this. What does that tell us? This actually tells us a lot of information. The range of the function A, okay, is going to, we just do isomorphisms before and after. So the isomorphism after is not going to change the dimension of the range, the minimal spanning set of it or anything. It's going to keep all that information intact. In fact, if we end up getting something like this, that means the dimension of the range of the output. Notice what the range of this matrix is. It's just, what can you get out in the output? It's just linear combinations of the columns. So it's basically the span of the columns. So the span of the columns clearly has dimension 2. It's spanned by these two guys, and those two guys make up a vector space. In fact, it makes up R2 as a subspace of this, and the first two components has dimension 2. So we can automatically say the range of A is dimension 2 by reading it off of this nice picture. So the dimension of the range of A is equal to 2. It's a vector space. The range is a vector space and it's dimension 2. Now, what about the dimension of the fiber over 0? Well, wait a minute, what's that? So let's suppose that A is a function, f, and let's think about this fiber here. This fiber is actually this fiber right here is actually a subspace of the domain R4. So it's a subspace of this. Sometimes it's called the null space. You could also call it the kernel of the map, of the function. And if we're taking a look at that, all right, and we want to know what the dimension of that, well, let's just think about running this right here. Just think of running the whole map right here, that, after we apply the isomorphisms and we get the simplified form of the function A after doing isomorphisms before and after the map. Let's think about what the fiber over 0 really looks like. That means, like, what do you input into this? So A, B, C, D, such that your output is going to be the 0 vector. Let's think. What does this mean? Well, apparently, notice that A and B are forced to be 0 here, right? So if in this matrix multiplication, we end up getting in this matrix multiplication right here, we can see that that the first entry is A. We matrix multiply. The next one is B, and then the next one is just simply 0. And so since these have to be equal in this set right here, this subset of the domain, the fiber over 0, what maps to 0 is this, we notice that A and B are forced to be 0. Okay. But guess what? C and D could have been anything they wanted to. In fact, they correspond to these two columns that have zeros. So we look at the number of 0 columns, and that's actually the dimension. You see, like, if you take any two ordered pairs C and D, that actually makes up a subspace of R4, which is isomorphic or looks a lot like R2, has dimension 2. So the number of these guys, these columns right here, that is the dimension of the kernel or the null space. So the dimension of the null space. Sometimes the range is actually thought of as the column space. Can you see why? Because it's just the span of the columns as vectors. So you can say the dimension of the column space is the number of ones that you see appearing right here in the simplified form. And the dimension of the null space or the kernel of the map, the fiber over 0, all those terms are the same, just different ways of saying the same thing, is 2. And we can see that directly from this. So what does this mean? Okay, well, this means that the matrix A takes a space of dimension 4 and squashes it to a flat plane of dimension 2. That's what it says. Um, that's pretty much what these guys say together. Notice also that you see the number of columns here is actually exactly equal to the dimension of the null space plus the dimension of the column space or the range. So you can think about that. So column space dimension or range dimension. So the dimension of the range plus the dimension of this fiber right here is always equal to the number of columns, which is the dimension of the range, the domain, that is. So like dimension of domain is equal to two things added together. This is one of the fundamental results that we use a lot in linear algebra. Um, but how do we get to it? How can we decide how to look at this matrix A and get this information from it? It's by doing these operations before and after. So stay tuned and we'll be practicing more of these. Thanks for watching.